for your kind introduction, Mr. Chairman. Ladies and gentlemen, good morning. I'm a master's student from National Chiao University in Hsinchu, Taiwan, and my name is Chia-Fong Chang. Today, my topic is about monolithic MEMS oscillator based on standard CMOS MEMS process. And this is how my presentation will go. I will begin with a background introduction, then move on to the resonator and circuit design considerations. After that, I will deal with the Oscillator Co-simulation and show you some measurement results. Finally, I will make some conclusions. And first of all, I would like to talk about some background. Silicon-based resonators have a great potential on multi-billion oscillator market for their compact size compared to the crystal oscillator. However, most of MEMS processes are incompatible with circuitry. Integrating microstructure with circuitry could further reduce the overall chip size for highly integrated SoC applications in portable devices. This work will present the monolithic MEMS oscillator for 32 kHz timing reference clock in consumer electronics. And here we are going to take a look at a fabrication process. After the ordinary CMOS process, the passivation layer above the predefined MEMS mark region will be removed. And the metal 7 layer was a hard mask for preserving the resonator body after the succeeding 2 dry etching steps. And the next figure shows you the anisotropic etching step, and the circuitry part was coated with photoresistor for protection. And finally, the resonator body will be released by the isotropic substrate etching and become a movable structure. All these processing steps complete inside fab without any post-processing like wet etching in laboratory. Therefore, highly SoC integration and mass production could be achieved through this standard process. And these figures illustrate the CMOS MEMS process and the electrostatic actuation by the cross-section view of the proposed resonator design. So now we move on to the mechanical resonator design. For monolithic integration, the 4 anchors were placed at corners to avoid wire bonding. And the 4 symmetrical springs were connected to anchors through 2 clamp beams. Such architecture could provide another degree of freedom to release the residual stress. And the white line interferometer had shown smaller curvature as expected. And this slide illustrates the cause of electrostatic spring softening effect. Equation 1 shows the electrostatic spring constant that leads to such effect, and we try to lessen it through comb-finger transducer. As you can see in equation 2, the comb-finger transducer shows relatively constant C2X derivative compared to parallel plate 1, since its movement direction won't change the gap D0. This property makes its absolute value of second-order derivative become nearly 0 and eliminates the effect to first order. To get the full benefits of both type transducers, I choose comb-finger as driving electrode and for frequency stability, and the parallel plate as tuning electrode for wide frequency tuning range. Now we move on to the circuit design. And this slide shows the TIA circuit architecture firstly demonstrated in reference 6 by Mr. Rosavi. And by comparing the denominator of the closed-loop transfer function with second-order system standard form below, the OP amplifier bandwidth omega A could be solved as equation 3 for maximum flat response. However, such requirement was too strict to reach for low-power design. And we made omega A lower than that to have a second-order underdamping system. Since the overall system is going to oscillate eventually, it's not necessary to eliminate all the effect through maximum flat response, but can somewhat be tolerant. And this figure is the second stage of the TIA circuit in previous slide and illustrates the capacitive source degeneration technique. Since the bias current IB was not ideal, it could be replaced by resistance RS in parallel with an ideal current. The GM transfer function shows an inductive characteristic. And since it introduced a 0 before a pole, and it could be used to ensure the system bandwidth on the low power design. And this figure shows the pulsing frequency response of TIA circuit. The solid blue curve was the magnitude response in decibel ohm, while the dashed red curve is the phase response. Here the inductive peaking was caused by the circuit technique mentioned before, so the bandwidth had been improved and the phase shift and target frequency was optimized as close as 0 degree. And this figure basically tells you the signal flow and the configuration of MEMS resonator for loop gain test co-simulation. If a non-sinusoidal signal, say square wave, was applied to the MEMS resonator, the output signal will become nearly sinusoidal. Due to this characteristic, the MEMS resonator could be modeled as a bandpass filter with extremely narrow passband and high insertion loss. So the TIA circuit should not only provide high gain to overcome the insertion loss, but also nearly 0 degree phase shift to ensure positive feedback as an oscillator. And here is the loop gain test co-simulation taken from the output of TIA. We have the loop gain greater than 0 decibel for oscillator system requirement. And here are the MEMS motion analyzer measurements set up under atmosphere pressure and vacuum respectively. We put a die on the piezoelectric patch, then use microscope to analyze the motion and frequency response of resonator. And this video shows the motion analysis of test key under atmosphere pressure. And this video shows the obvious motion inside vacuum chamber. And this slide shows the comparison between two resonator designs with nearly equal resonant frequency but different spring length and turns. Design 2 has the lower quality factor since long spring suffers from more air damping. However, it has less residual stress problem due to shorter shutter and also has better signal strength due to more sensing fingers. Besides, the quality factor of the two designs become quite close under vacuum. It is also worth mentioning that the resonator field with tungsten wire has higher quality factor. Therefore, design 2 was chosen to be the proposed resonator design. Maybe the computer is shut down. And this slide shows the frequency response measured by MEMS motion analyzer under atmosphere pressure. The quality factor seems to be quite consistent, while the resonant frequency was slightly deviated from simulation. Because the layout was built with tungsten wire between different metal layers and the mass was under mathematics in FEM simulation. And this slide shows the measurement under 32 Pascal pressure. Here we may notice the huge discrepancy in quality factor. The reason might be the vacuum chamber full of oil molecules from the oil rotary vane vacuum pump, which will greatly degrade the quality factor. And this slide shows the photograph taken by wide-line interferometer, and the table below summarize the overlap percentage in different parts. The finger shows high overlap percentage since design tool was chosen, and the CC beam shows the lowest overlap percentage as expected since it was designed for compensating the residual stress from other parts. Here shows the comparison table. Even though the quality factor of this work is the lowest, the pressure was the highest due to non-perfect airtightness of vacuum chamber. Besides, this work is the only one could monolithically integrate through standard process in this table. Well, this brings us to the end of my presentation. Let's see what we may conclude here. This work presents a monolithic MEMS oscillator 20 times smaller than crystal oscillator and has better system integration ability. The TIA adopts capacitive source degeneration technique to achieve low power design, and the proposed resonator structure was designed for frequency stability, wide frequency tuning range, and low residual stress. And we still find tungsten wire could help improve the quality factor. That's all, thank you, and I will be really interested in taking your questions.